17.2 Conservation of mechanical energy. We start with the definition of the word system. In physics, a system refers to a collection of connected parts forming a whole. For example, the Earth, which is made up of many different parts, is considered to be a system. An isolated system is a really important concept in physics. In physics, an isolated system is a system that does not exchange matter or energy with its surroundings. The concept of an isolated system is a little bit idealistic. There's really no such thing as an isolated system in real life. Isolated means that nothing can enter or exit. And we know that that's actually impossible. Even the Earth isn't an isolated system because sunlight and the energy from the sun enters the Earth. An isolated system must also be frictionless, and it's impossible in the real world to actually have a frictionless system. For that reason, isolated systems are kind of ideal, but they're easier to do calculations for, so we use them as a concept. Isolated systems are critical for understanding the law of conservation of energy. This law only applies in an isolated system. The law of conservation of energy says that in an isolated system, the total amount of energy remains the same. Conservation means staying the same. So conservation of energy means the total amount of energy stays the same. This doesn't mean that energy can't change forms within the system, but it does mean the total amount when you add all the energies in all types together must be the same. Kinetic energy can turn to potential, and potential energy can turn to kinetic. But the law of conservation of energy says that the total mechanical energy, which is EM, which is equal to the kinetic energy plus the potential energy, must remain the same. Here's an example that shows the law of conservation of energy in action. As the ball rolls down the track, notice that the yellow bar, the total mechanical energy, remains the same. The potential slowly converts into kinetic as the ball goes down the track, and as it travels back up again, the kinetic decreases and the potential increases again. Kinetic and potential exchange and transfer into each other, but mechanical energy remains the same. So if we consider the same track again, at the very top where the ball is placed, we're going to call this the maximum height. When the ball is just placed at the maximum height, the initial kinetic energy is 0. Let's set the mechanical energy to be 10 joules, just for the purpose of the example. Since the kinetic energy is 0 at this maximum point, that means the potential energy must be 10, because 10 plus 0 equals 10. Halfway down, half of the potential energy has been converted into kinetic energy. The mechanical energy, according to the law of conservation of energy, must remain the same. It's 10 joules still. The kinetic energy is now 5 joules because the ball is sped up, and the potential energy has decreased accordingly. 5 plus 5 still makes 10. When the ball gets to the very bottom at the ground, the height is 0 meters. The mechanical energy is still 10 joules. But Since the height is 0, the potential energy must be 0 joules, which means the kinetic energy must be the total 10 joules, because 10 plus 0 makes 10. Partway back up again, we have a mix of kinetic and potential energy. But the mechanical energy must still equal 10 joules, so the potential energy and the kinetic energy must add to equal 10. At this point, let's say that the potential energy is 3 joules. This means that the kinetic energy would have to be 7 joules, because 7 plus 3 equals 10. The law of conservation of energy says that kinetic and potential can change, but the total mechanical energy has to be the same at all points in an isolated system. Here's an example that uses numbers and allows you to calculate the speed at a different point. Here's another roller coaster track. We're going to call point A having a height of 1.5 meters, and point B, HB, has a height of 0.5 meters. A 2.5 kilogram cart is placed at point A on the track shown below. How fast is it going at point B? Here's how we do this calculation. We know that the mechanical energy at point B must equal the mechanical energy at point A because of the law of conservation of energy. That means the potential energy at A plus the kinetic energy at A must equal the potential energy at B plus the kinetic energy at B. We know at point A because the cart was just placed on it, it had no speed, therefore the kinetic energy at point A was 0. Rearranging, we can find the kinetic energy at point B equals the potential energy at A minus the potential energy at B. So the kinetic energy at B is the potential energy, which is mgh, which is 2.5 times 9.81 times 1.5 for point A, minus mgh for B, which is 2.5 times 9.81 times 0.5 for point B. This gives us a kinetic energy at point B equal to 24.525 joules. We can use this kinetic energy to find the speed at point B, because the kinetic energy formula is EK equals 1/2 mv squared. This can be rearranged for v to be the square root of 2ek divided by m. V is square root 2 times 24.525 divided by the mass of 2.5 kilograms, which gives us 4.4 meters per second. Now, it's important to realize in these calculations that mass doesn't actually matter. And this is true for most conservation of energy calculations. I'll show you why. If you have 2 points, A and B, the mechanical energy at point A will be equal to the mechanical energy at point B as long as we're working with an isolated system. So EPA plus EKA equals EPB plus EKB. Writing out the formulas in full, we have MGHA plus 1/2 MVA squared equals MGHB plus 1/2 MVB squared. Notice that all of these formulas have m in them. If we divide each one by m, we see that m cancels out. So you don't actually need m to do the calculation properly. Here's an example. The nice thing about this example is I'm going to do an inclined plane problem without having to do all the vector addition that we did when we looked at forces. Here's an inclined plane where an object is sliding down an incline from point A to point B. The height at point A is 0.75 meters, and the height at point B is 0 meters. We don't even need to know the angle of the incline because energy is not a vector, it's a scalar, so direction doesn't matter. We just want to know how fast is the block sliding at point B, and we can use conservation of energy to solve this. We know the mechanical energy at point A equals the mechanical energy at point B. This means mgha plus 1/2 mva squared equals mghb plus 1/2 mvb squared. And mass cancels out across the whole formula because it's in each term. This becomes 9.81 times 0.75 for point A plus 1/2 5 squared equals 9.81 times 0, which is the height at point B, times 1/2 plus 1/2 VB squared. This gives us 19.865 joules equals 1/2 VB squared. VB equals 6.3 meters per second.